Good afternoon, friends. I am Sridhar Swami from National College, Jayanagar, Bangalore. Today, we shall discuss about the nuclear reaction. Like many other reactions, nuclear reactions too are similar to that of chemical reactions and other such reactions. Now, what exactly is the description of a nuclear reaction? We shall see. It's a process in which an energetic particle is targeted towards a nucleus to produce certain changes in the target. You can see in the diagram a particle being aimed at moving towards a target nucleus, and after some time you can see the residual nucleus is moving along a specific direction, leaving aside an ejectile or a particle which is coming out of the nuclear reaction. The particle which is targeted towards a specific nucleus, we call that as projectile. And it is the target nucleus which receives the projectile, gets collided, and after that, whatever the transformed nucleus which we get, we call that as residual nucleus, and finally the particle which is coming out of the reaction is known as ejectile. Let us take a very simple example where an alpha particle is projected towards a nitrogen nucleus. Now, as a consequence, we can see oxygen 17 is formed, leaving behind one proton. Now, the alpha particle which is colliding with the nitrogen nucleus, we call that as projectile. The nitrogen nucleus which is targeted is known as target nucleus, and the changed nucleus which we call oxygen here in this case is the residual nucleus, and apart from this residual formation of the residual nucleus we have a proton getting out in the form of an ejectile. So like this we have an alpha particle being the projectile and proton is the ejectile. Now, when you think of a nuclear reaction, there are two possible types. So, one we call direct nuclear reaction, where the initial step to final step take place in the reaction directly or instantly. It is in a single step. Whereas, in case of some other reactions, you can see there is a formation of an intermediate state. The projectile is absorbed by the target nucleus and it will be converting into a compound nucleus. The compound nucleus, which will be a short-lived one, which will be in an excited state, will be de-excited to form a residual nucleus along with the ejection of an ejectile. Now, depending upon the energy exchange, it is also possible for us to have two distinct types of nuclear reactions. So, one we call elastic scattering. Here, the incident particle strikes the target nucleus and leaves without any exchange of energy. You can see here in this case of alpha scattering of Rutherford, where many alpha particles they were just moving aside, changing the direction from the target gold foil. This is an example of elastic scattering. But we also have certain nuclear reactions wherein we can find inelastic scattering. The incident particle strikes the target nucleus and leaves after exchanging energy with the target nucleus. But interestingly, we can see that only there is an exchange of energy between the projectile and the nucleus. Now, as a consequence, we can see the projectile and ejectile being of the same nature. However, there will be a change in the energy because of the exchange of energy between the projectile and the target nucleus. Now, when you think of other types of nuclear reactions, we have here a very simple one in the form of a radiative capture. Now here in this case, the incident particle is captured by the target nucleus to form a new nucleus. The ejectile here being just the energy. Now you can see the case of a proton being targeting towards magnesium. Now as a consequence, the proton gets absorbed by the magnesium and will be transformed to aluminum nucleus. But in the process, we can see there is an ejection of gamma particle. This is an example of radiative capture. Now we can also think of another example of a nuclear reaction, that is disintegration nuclear reaction. Here the target nucleus captures one of the constituents of the projectile. In the earlier case, we saw the entire absorption of the projectile. But here the small portion, a part of the projectile is being absorbed by the target nucleus, forming the residual one, and the remnant of that will be ejected in the form of an ejectile. So you can see here an example where an alpha particle is bombarded to a beryllium nucleus. Now as a consequence, out of the 4 nucleons of helium nucleus will be absorbed by the beryllium to form carbon 12, and the remaining nucleus will be ejected out in the form of an ejectile. So like this we can see a part of the projectile is being absorbed. We can also see another important thing wherein we can find the exchange happens in a reverse way. That is, we call photodisintegration nuclear reaction. You think of a gamma ray photon being bombarded to deuteron. Now, as it hits the deuteron nucleus, we can see there is a decomposition and we can observe a proton and a neutron coming out. Now, the deuteron will lose a nucleon, and as a consequence, a neutron will be emerging out. So, like this, we can see the photon which is incidenting there in the form of a projectile will take some part of the target nucleus, which is a reverse process of disintegration. We call this as photodisintegration nuclear reaction. Like all the various reactions in physics, we have a conservation laws being satisfied in nuclear reactions too. What are the conservation laws in nuclear reaction? We shall see here. Now we know that in all the reactions we can see the conservation of charge, linear momentum, angular momentum, parity, nuclear number, mass number, spin. These are the physical quantities which are conserved during a nuclear reaction. However, the rest mass energy and kinetic energy, they are not separately conserved. Let us see how it is. Let us look into the conservation of nuclear number. If we just look into this example, we can see the reactants are alpha particle and the nitrogen, where we have 18 is the total nuclear number, and on the other hand we have in the form of products oxygen and hydrogen, where again 17 and 118 is the nuclear number of the product. In the same way, we can also think of conservation of mass number. So nuclear number, of course, is identical to the mass number. We can see the total A is also conserved. In this example quoted here, the hydrogen, carbon, and other reactants, where 13 is the mass number of the reactants, total mass, and on the right hand side again this N13, that is also the same as the mass number of the reactants. That is how we can see the conservation of mass number. Now on the same lines we can think of conservation of spin, conservation of linear momentum, conservation of angular momentum. Now let us look into an important aspect of conservation of energy. We know that the energy will be existing in the form of mass 2, which we call rest mass energy. It is not just the kinetic energy of the particle, but also the rest mass energy. So this has to be taken into account while thinking of the energy conservation principle in case of nuclear reaction. So we can say roughly it is just the equaling of, or the equivalence of the net energy before collision or before the nuclear reaction and net energy after the reaction. That is total energy of the parent nucleus and the bombarding particle, including the rest mass energy and kinetic energy, is equal to the total energy of the residual nucleus and the ejected particle. So this is how we can see the conservation principle of energy will be satisfying in the case of nuclear reaction. Now let us look into an interesting aspect, an important aspect of a nuclear reaction. This nuclear reaction will be, which is having this energy exchange, will be producing a distinct value of Q, which we call Q value of a nuclear reaction. Now, what is this Q value of a nuclear reaction? Let us see this description or the definition. So, Q value of a nuclear reaction is the difference between the total rest mass energy of the reactants and the other products. Now, we know that a reactant has nothing but the projectile at the target nucleus and m1c square. If you consider m1 as the mass of the projectile and m0 as that of the target nucleus, then m1c square will be the rest mass energy of the projectile, m0 c square, that is the target nucleus. We can say them as the sum of the energy of the reactants. On the other hand, let us imagine that there is a projectile whose mass is m2 and the residual nucleus will have a mass m3, thereby m2c square and m3c square happens to be the net rest mass energies of the products. Now, according to the energy conservation principle, we can see the difference between these rest mass energies is given by Q value. Now let us look into a very simple relationship for Q value. This is how we will derive the Q value of a nuclear reaction. Let us consider a projectile whose mass is m1, momentum is p1 and kinetic energy is e1. Let it be moving towards a target whose rest mass energy is m0. Now after the reaction, the residual nucleus will fly away in the direction phi along the direction making an angle phi with the initial x direction. In the same way, let us consider the projectile being moving in a direction making an angle theta with the initial direction. Let m2 be the mass of the projectile, p2 its momentum, e2 its kinetic energy. On the same lines, let m3 be its mass of the residual nucleus and p3 its momentum and e3 its kinetic energy. Now, when you are looking for the Q value derivation, we can see from law of conservation of energy, the total energy of the reactants should be equal to total energy of the products. Now, m1c square, which is the rest mass energy of the projectile, even its kinetic energy, and m0c square, rest mass energy of the target nucleus together will make up the net energy of the reactants. Similarly, the net energy of the products will be m2c square, that is the rest mass energy of the ejectile, e2 its kinetic energy, m3c square rest mass energy of the residual nucleus and e3 its kinetic energy. So we can see the law of conservation principle will give us this equation. Rearranging this, we can very easily come to a conclusion that the Q value, whatever we have discussed earlier, is nothing but E2 plus E3 minus E1. Now, we can derive this further by using the law of conservation of linear momentum. Now, we know that the momenta of the ejectile and that of the residual nucleus, which are along a specific direction, can be computed in terms of their components, and thereby we can see along the horizontal direction we have P2 cos theta and P3 cos theta, P3 cos phi, or P2 sin theta and P3 sin phi along vertical directions. By looking into the conservation of linear momentum principle, we can have these two equations and thereby we can rearrange this to arrive at P3 cos phi being is equal to P1 minus P2 cos theta, P3 sin phi is equal to P2 sin theta. According to law of conservation of linear momentum, we can think of the conservation principle along horizontal direction and vertical direction separately. Now squaring and adding these two equations, we get P3 square is equal to P1 square plus P2 square minus 2P into cos theta. But the momentum of a particle, which is nothing but m into v, can also be described in terms of square root of 2me. Thereby, we can substitute it for P1, substitute for P2, and use it for P3. Using them, we arrive at a simple expression for E3 in the form of equation 5. Now, using this value of E3 in equation 1, we arrive at the Q value, which is equal to E2 into 1 plus M2 by M3 plus E1 into M1 by M3 minus 1 minus 2 by M3 into 2 M1 M2 even E2 raised to half into cos theta. So we can see here the Q value of a nuclear reaction not only depends upon these three masses M1, M2, M3, and apart from that, the kinetic energies and the angle by which the projectile has been moving. Now, interestingly, we can see here the Q value can be positive or can be negative. Let us look into these two distinct cases. Now, supposing, let us say Q is positive, that is Q is more than 0. Now, in this case, energy is released during the nuclear reaction. We call this as exergic nuclear reaction. Now, interesting part of this is energy of the reactants is more than that of the products. On the same way, supposing it is negative, then the energy is absorbed during the nuclear reaction, which we call endoergic nuclear reaction, where energy of the reactants is less than that of the products. So like this, depending upon whether Q is positive or negative, we have exergic as well as endoergic nuclear reactions. Now, let us see an interesting aspect of the endoergic reaction where we have threshold energy. What is this threshold energy? It's a minimum kinetic energy of the projectile required to initiate the nuclear reaction. Supposing we have an endoergic reaction wherein we need to provide energy to the target nucleus so as to see that the conversion in this reaction is taking place. So this initiation is essential, and because of that the projectile has to have a minimum energy. Let us look for the expression for threshold energy. For that we will consider the projectile M1 whose mass is M1 and a target nucleus whose mass is M2. And for time being, let us consider that because of the collision, they get collapsed and move together with a compound nucleus. If mc is the mass of the compound nucleus and v c its velocity in the same direction, we can write using the conservation of momentum principle that m1 v1 is equal to mc vc or vc is equal to m1 v1 by mc. Now, let us look for the threshold energy. We can show that the threshold energy can be written also as minus q is equal to half m1 v1 square minus half mc vc square. By taking m1 v1 square, substituting for vc and taking out m1 v1 square by 2, we can arrive at a very simple relation for the minus q value, and finally we can rewrite for half m1 v1 square. Now, what is half m1 v1 square? It is nothing but the kinetic energy of the projectile which is producing or initiating a nuclear reaction, which can be termed as threshold energy. Thus, we can see the threshold energy is equal to minus q into 1 plus m1 by m2. So, thus, we notice that the m1 and m2 will decide the value of q and value of ETH, that is threshold energy.